Hey, good afternoon, everyone. So today's lecture is pre-recorded because of my absence, because I am now on a conference. So today we will start with a description of specific types of lasers. So let's say we are enough of theory. So I will not speak about fundamentals and physics of lasers, but now I will just describe certain types of lasers. But please remember from the, let's say, the first part of this lecture, of this entire course, some fundamentals of the laser physics. So elementary transitions that occur in media and quantum media, the conditions how to obtain gain in quantum amplifiers, so the definition of population inversion and how to get population inversion. Also the differences between a 3 and 4 level systems. We also describe the fundamental parameters of optical resonators. So you should be able to just draw a schematic of a Fabry-Perot resonator and write the fundamental parameters of them and distinguish what are the longitudinal and transverse modes. And what does it mean that the laser is single mode and multimode? And also the thing that I was mentioning last time, so the line broadening mechanisms. Okay, so today we will quickly just go through the types of lasers, and I will start with the gas lasers. And if I have enough time, I will maybe make a short introduction to semiconductor lasers. So generally, we distinguish many types of lasers, and we just classify them into groups depending on the type of the gain media that they are using. So we can distinguish, for example, gas lasers. So as you can guess, the active medium is just a gas, right? So it might be either an atomic gas, where we have just atoms of gases. So for example, noble gases like neon. Or we have molecular lasers, where the gas consists of molecules, for example, CO2, so carbon dioxide, or carbon oxide, CO. Sometimes these gases might be ionized, so then we have a subgroup of atomic lasers, which are ion lasers. So they are just atoms but ionized. In case of molecules, we can also distinguish excimer lasers. So excimers are some kind of combinations, compounds of noble gases, like kryptonium fluoride, argon fluoride, xenon chlorine, and so on. So these compounds exist only in the excited state. So they don't exist like in natural ground state, but they can exist only when they are excited. A second group, chemical lasers. So these are lasers based on some liquid media very often, and they are based on chemical reactions. So for example, there might be a reaction between hydrogen and fluoride, and these reactions release a great amount of energy, and these atoms can then generate light from these excited states. Dye lasers relate to also lasers that are based on some liquid media, which are organic dyes. For example, rhodamine is one of these most popular dyes. It emits light in the red color. So mostly, in most of the cases, dye lasers generate visible radiation. The next group are free electron lasers. So these are just lasers based on high-speed electrons that are moving in magnetic field. And these are huge infrastructures because it requires these accelerators and so on. So these are like huge rings that have over hundreds of meters where they accelerate these electrons, and they generate a very broadband spectrum, but mostly in the UV range. A huge group of lasers are the solid state lasers. So this group is related to lasers where the active medium is just based on some solid state medium. So this might be just a piece of glass or a crystal that is doped with optically active elements, for example, lanthanides like erbium, ytterbium, thulium, holmium, praseodymium, neodymium, and so on. And they can be pumped with lamps or different types of lasers. So we use optical pumping there. Another subgroup of solid state lasers are fiber lasers. So the gain medium is just an optical fiber. So we have the fiber and the core of the active fiber is doped with one of these materials, the same as in just bulk solid state lasers based on crystals, and they can emit light. Another subgroup, disc lasers, where the medium has the form of a thin disc. So the disc can have like millimeters or even centimeters of diameter, but the thickness of the disc is really small. So at the level of let's say 100, 200 micrometers. And the most numerous of all lasers, semiconductor lasers, they are the most popular lasers, and we can also distinguish them into some smaller groups, like low power signal lasers used in, for example, in the telecom. So when you have high speed broadband internet at home from the fiber, then you always have also a laser in your switch, in your router, because you also transmit data in the other direction, right? So you have a laser there, a small power semiconductor laser. We have also high power lasers like 10, 20, 30, 100, 500 watts of output power that can be used directly for processing of materials, or they can be used as pumps for other types of lasers. We have a group of mid-infrared lasers. So this is a specific group of lasers which are based on some kind of different technology, and they generate mid-infrared light. So light from the range above 3 micrometers, and they are so-called quantum cascade lasers, QCLs, or interband cascade lasers, ICLs. And other lasers like VCSELs. So this is a group of lasers with a vertical cavity. So the beam is not emitted from the edge of the semiconductor, but from the top layer of the semiconductor. So VCSEL stands for vertical cavity surface emitting laser, and VCSEL is the vertical external cavity surface emitting laser. So they emit from the surface. There's a hole in the surface of the semiconductor, and it emits light from this hole. So just as a quick reminder, we will define some of the basic parameters of lasers. So just to quickly conclude these parameters. So the most important parameters is of course the wavelength or the frequency of the laser emission. So we express it in nanometers if we speak in wavelength, or in hertz or terahertz usually if we express it in the frequency domain. So let's say central frequency in terahertz, for example. And we define the spectral bandwidth. So the bandwidth is the width of the emission line at half of its maximum. So we already know the mechanisms of broadening of these lines. Usually if the line is very narrow, then we express it in the frequency domain. Using this formula, we can switch between wavelength and the frequency, and it's good to be able to recalculate between these two units. So as an example, if we have a helium neon laser that emits light at the wavelength of 632.8 nanometers, this corresponds to a frequency of 474 terahertz. Okay, so this is C over lambda. This will be 474 terahertz. And for example, if we assume a usual line width of a helium neon laser at the level of 100 kilohertz, if we recalculate it to the wavelength domain using this formula, we will get that the line width expressed in wavelengths, in nanometers, is equal to 1.3 times 10 to minus 7 nanometers. So this is a, let's say, a very small number. That's why it's way more convenient to express it in the frequency domain, because then we just say 100 kilohertz, which is a nice round number, instead of saying 1.3 times 10 to minus 7 nanometers, like picometers or something like that, right? So when we speak about lasers that have a very narrow line, we definitely use the frequency domain, but we express the central wavelength in nanometers, right? The second most important parameter of the laser is, of course, the power. So if the power is constant, I mean, if the laser is a so-called CW, right? So continuous wave laser, it generates constantly the same power. So we can just say that the power is equal to, let's say, 1 watt. But if the laser is pulsed, then we have to define more parameters of the pulses, like the pulse duration. So this is the pulse duration here, measured in also half width of full width at half maximum. We define the pulse repetition rate. So this is the repetition rate or repetition frequency. So how often the pulses are repeating at the output of the laser. We can also express it like the pulse to pulse time. However, definitely more often we use the repetition frequency rather than pulse to pulse time. From that, we can calculate the pulse energy. So the pulse energy is just the energy stored inside one of the pulse, right? So you can calculate that by averaging the power. So then we define the average power. And when we divide the average power by repetition frequency, we can get the pulse energy. And the pulse peak power equals to the energy over time, so the pulse duration. Yeah, so these are the basic parameters of the pulse laser. We have some more, we can define more general parameters of lasers, like power stability or frequency stability, that describe the variation over time and the stability. So we use some statistic measures to define the stability, like RMS or whatever. We also define the polarization, so we can have a linear or circular or just random, which just means in general elliptical polarization. It's important to define the beam quality, and when defining the beam quality, one can use the m-squared parameter. So I already mentioned about the m-squared parameter. So this is the parameter that shows us how close to an ideal Gaussian beam our beam is. So that's just a measure of how close to a Gaussian beam we are. We can define the divergence, usually expressed in milliradians. So for example, if the divergence equals 1 milliradian, it means that the beam gets bigger by 1 millimeter over 1 meter of propagation. And sometimes manufacturers also define the spot size. So this is the size of the beam at the output of the laser, for example, measured at the output aperture of the laser. And of course, the spectral coverage of lasers in general spans from the UV until the infrared spectral range, so even to the far infrared. And the visible part is just a very tiny slice of the entire electromagnetic spectrum. But when we speak about lasers, we have lasers between the UV and the infrared. So we will start with gas lasers today. So generally, a gas laser is a laser in which the emission occurs from atoms in the form of a gas, and we induce an electric discharge in this gas to produce the light. So the electric discharge causes releasing of a huge amount of energy, and this energy, I mean, the atoms are excited because of this discharge, and then when they are already excited, we just break this thermal equilibrium, and we can induce population inversion and obtain emission. And the first gas laser was the helium neon laser, operating at the wavelength of 1150 nanometers. So this is not the most common wavelength for a helium neon laser now, because now the common wavelength is 632.8. This is the most popular helium neon laser wavelength, which is used in metrology, interferometry, and many other applications. So the first gas laser was developed by Ali Javan and William Bennett in 1960. And they were not the first guys to ever develop a laser, because the first laser was demonstrated by Theodor Maiman, and this was a solid-state laser, a ruby laser, actually. So they were a little bit late. They demonstrated the gas laser a few months after the Maiman's discovery. And probably this was because a gas laser is a way more complicated system than a solid state laser, because you need to care about a lot of parameters. There are a lot of degrees of freedom in gas lasers. Nevertheless, they are still developed since the 1960s. Especially CO2 lasers are still under development. So there are still some new inventions in this area. However, as you can guess, it already saturated a little bit. So nowadays people concentrate on totally different lasers, like solid states, for example, and semiconductors, not necessarily gas lasers. And among gas lasers, we distinguish atomic lasers, ion lasers, molecular lasers, and external lasers. So why they are so interesting? So there are several reasons why people were focusing on gas lasers. So the most important thing in gas lasers is that they are characterized by a very narrow emission line. This is because the long transition lifetime in atoms of gases, what I was talking last week. So this translates into a very narrow emission line and a limited, let's say, influence of the line broadening mechanism, like natural broadening. So that's why they are used nowadays in many applications. That's the main reason. So their emission line is, let's say, very close to a monochromatic line. So we have a lot of degrees of freedom. So we can shape the laser cavity. Okay, so we can scale the length, the area, the volume. So if we want to increase the power, we can make a bigger volume. They have an extraordinary lifetime, so long lifetime. So they can be used for a few decades like helium neon lasers, without any degradation. If there occurs some degradation, we can just recycle the gas, so just exchange the mixture and they work again. There exists some lasers that have the possibility of a flow of the gain medium. So this enables just refreshing of the medium and removing the heat. We can mix different ratios, mix different gases in different ratios and different pressures. So to form the gas media with different parameters. Yeah, and as I said, they are characterized by very narrow, well-defined spectral emission bands. So the metrological standards that are used as like for frequency metrology or dimensional metrology, they are very often based on gas lasers. And we have a great number of different gas media that cover almost the entire spectrum from the UV up to the infrared. Okay, so we have excimer that generate light in the UV range. We have a lot of compositions, mixtures that can generate visible light and also the infrared light. And some of the gas lasers can generate even very far infrared, like methanol. You can see these are even millimeter waves. So with gas lasers, we can cover almost the entire optical, let's say the optical bandwidth. Yeah, however, these also the advantages that I am listing here, they are very often also a problem, an issue, because there are too many degrees of freedom. So they have also some disadvantages. So first of all, we need just very developed vacuum technology, because we need to firstly ensure that our tube, that our capillary that we will fill with the gas, it needs to be emptied. So we need to firstly have a pump, make the vacuum, and then we can pump in our gas. And we need to care about the concentration. We need to care about the pressure, the mixing ratio, and so on and so on. So we need to also have a powerful power supply, because we need to induce the discharge. So for that, we need high voltages. So high voltage power supplies, like kilovolt range or even more. So there are so many degrees of freedom, and the resonators are quite bulky because they are made of glass. We need the glass capillary that we will fill with the gas. So it's a very inconvenient way of making a laser. Nevertheless, they are still used and still developed and still manufactured because of the probably main reason that they are very stable. They have a very narrow and well-defined emission line, and they have a extremely long lifetime. Yeah, among the more the most important disadvantages, yeah, the low efficiency is also a disadvantage. So in case of Heine laser, we have less than 0.1% of efficiency sometimes. However, on the other hand, we get a beautiful, very narrow spectral line. So the construction might be bulky, so you can see the typical construction of a Heine laser. So this one on the left-hand side is a laser with external mirrors. So we have the capillary with the helium and neon, and the mirrors should be here and somewhere here. So we just align the mirrors separately, and the tube is just something which is separated from the resonator. Here, the second one is the integrated tube, where we have the mirrors directly bonded on the tube. So the tube has just mirrors glued on both ends, for example. Yeah, so this is the typical structure, typical schematic of a helium neon laser. So I will start the description of gas lasers on the example of a helium neon laser. Then I will move to a CO2, but in generally the let's say the construction of most of the gas lasers is very similar. So the helium neon laser is a very nice example to describe just the structure of and the working principle of gas lasers. So we have the capillary. So our tube, which is filled with the gas, with the atoms, in let's say very low pressure usually. And we have an anode and a cathode where we just will connect our power supply. And in this first case, so the resonator is is just an external device. So we have external mirrors that are, let's say, independent on the capillary. So they are just surround the capillary here. So we can build a confocal resonator or anything. We can align these mirrors. And the tube contains also Brewster windows. So these are, I will explain it in a few slides why we use Brewster windows, but these are just the exit windows. So light is just exiting the tube through these windows, and they are placed under some certain angle with respect to the optical axis. We can also have a compact construction of the helium neon laser where the mirrors are directly glued, for example, with the capillary. So they are directly mounted on both ends of the capillary. So here we don't have to align anything. This is just factory aligned and just bonded together, so we don't touch it. It will work forever. And we also have the anode and the cathode. So we just connect the power supply to that. And the capillary is filled with the gas mixture. So the typical parameters that we have in helium neon lasers are the following. So the pressure of the gas is very low. So this is because the collisional broadening, what I was mentioning last time. So when we decrease the pressure, we reduce the probability of collisions between the atoms, and that's why we decrease the line broadening, right? Because if we increase the pressure, then we have pressure broadening, and we can increase the line width. So typically the pressure is around 1-2 torrs. So a very low pressure. The ratio of helium to neon is at the level of 10:1. So we have definitely more helium atoms than neon, but neon is responsible for the emission. Okay, so the light is generated by neon atoms. Helium is just only to fill the tube and to provide the energy to neon, because in the process of discharge, we excite the helium atoms and then they transfer the energy to neon. A typical length of the resonator is at the level of some tenths of centimeters. So this depends on the application and so on. But usually shortest lasers are at the level of, let's say, 20 centimeters. But you can also buy longer lasers. They usually have a higher power. But you need to remember that if you make a longer tube, then you reduce the free spectral range, and you can have more longitudinal modes generated in your spectrum, because the gain, the width of the of the gain curve in helium neon laser is at the level of 1.5 gigahertz. So when we have a long laser where we have like less than 100 megahertz of mode spacing, we can have many modes, many longitudinal modes emitted from the laser. So regarding the power supply, we need at least 2 kilovolts of voltage and a low current of a few milliamps. So this in total gives us the delivered electrical power at the level of 10 watts typically. So we deliver approximately 10 watts to the laser, but in turn we get like 1 milliwatt of output power, okay? So the efficiency is, very low at the level of 0.1%. So the efficiency is very low. The construction is quite difficult, but we, on the other hand, we in turn can get a very beautiful emission line, which is very narrow. And if we make the laser properly, we can get a TEM00 fundamental transverse mode and a single frequency operation, which is very useful in applications like metrology. So regarding the wavelength, we can choose between plenty of transitions that are possible in neon atoms that correspond to different wavelengths. So here you can also see the intensities of these transitions. These are relative intensities which are normalized to the most powerful transition of 632.8 nanometers, which is just a typical red color generated from this helium neon laser. So you can see this laser also on the laboratory. On the lab, we have also, as far as I remember, a yellow or orange laser, which is 611. And we have also a green laser, which is 543 nanometers. However, there exists, of course, other possible transitions. And there are also these 3 transitions in the infrared. So the mid-infrared transition at around 3.39 micrometers. Infrared transition at 1.52. So this overlaps a little bit with the telecommunication window. And the first, let's say first transition, so this is the 1.15 micrometers in the infrared. So you can see that we can cover a pretty nice, pretty broad range from the yellow up to the infrared with helium neon, depending on which transition we choose, right? So we can select these transitions by, of course, designing the laser, designing the mixture and so on, but also by choosing mirrors that will just discriminate the other transitions. So we just use mirrors that will reflect the specific wavelength. So this is the energy level diagram of helium neon medium that explains us how this laser is actually working. So as I said, we pump the helium atoms. So here we have the energy levels of helium. So by applying the power supply and causing the excitation, the discharge in the gas, we excite helium. And here we have 2 possibilities. We can excite it either to this level, so 2,3s or 2,1s. And since so helium just absorbs this entire energy, and since the energy level lifetime of helium atoms is quite long, like even up to a second, it means that these atoms stay in this level for a long time. So we increase the probability of collisions between the helium and neon atom, right? So the helium atoms collide with neon, and they just transfer the energy to neon, causing population inversion in neon. Okay, so now we have population inversion in neon. We have excited neon atoms, and then we can generate photons from them. So depending on the wavelength where we want to work, we have different possibilities. So either we can use the 3.3 infrared transition, we can use the visible transitions here, or we can use the infrared first transition here, or the other visible transitions. So in general, this is something like a 4-level system, because we have the ground state, we have the upper state, we have the upper. Maybe we will mark it as 4. We have the upper laser levels, which are the 3 here, and we have a second level, which is above the ground state here. Okay, so this is the lower energy level of neon, but it is located above the ground state, right? So even if this level is filled, it can be emptied by, for example, collisions of the gas with the walls. So this causes relaxation to the ground state. So we can then assume that we have a small number of atoms on this state and a lot of atoms in the upper states. So we have population inversion. So in general, we can define this as a 4-level system with the energy transfer between the helium and neon. And this is a very common way of doing lasers. So we will have a lot of examples in the future when describing different types of lasers that we don't use only one atom in the gas medium, but we use 2 atoms, and one of them absorbs the energy and transfers the energy to the second one that is responsible for the emission. Yeah, so this is something I have already shown you. So these are the potential modes that can be generated from the helium neon laser, depending on the resonator configuration. So in the laboratory, we have lasers that unfortunately generate only the fundamental TEM00 mode. So we can't show you, probably we can't show you the higher order modes, but it's also possible to generate them. But in most of the cases, we want to have the TM00, right? However, it's get more complicated in the longitudinal. This should be longitudinal mode operation, because the gain curve, as I said, the gain curve is broad enough to support oscillation of many longitudinal modes. Okay, because this depends on the free spectral range of the resonator, so the separation between the longitudinal modes of the resonator, of the cavity. So if we assume that our cavity has equally spaced resonances, let's say at the level of 100 megahertz, and the gain curve is 1.5 gigahertz wide, then we can excite several longitudinal modes, right? Of course, we have some level of losses in the cavity. So losses because of, for example, reflectivity of the mirrors. We have some losses, but the gain curve overcompensates the losses. So here we cannot excite these modes that are below the level of the losses, right? So we don't excite these modes, but we can easily excite all these modes that are here. So they are over the loss and they are under the gain curve. So the spectrum of this kind of laser will look like that, right? So we will have 5 longitudinal modes in this specific case. And this is sometimes unwanted. Sometimes you want to have 1 longitudinal mode. That's why we need to make a very short resonator, short cavity. Then we will have a large mode spacing, and we will have only one mode under the gain curve, right? So we will have only one excited frequency of our laser. Yeah, this picture shows just a typical helium neon laser. So you can see this kind of lasers on the laboratory. Just a tube with the plug and the power supply, right? Yeah, it costs. Thorlabs is maybe not the best store where we would like to buy helium neon laser because it's quite expensive, but you can see that the cost is around 1,800 euros. And here you can see a screenshot of the basic parameters that the manufacturer is providing. The first parameter is polarization extinction ratio. So this parameter tells us what is the ratio of the polarized light in the output to the unpolarized. So we have 500 times more of polarized with respect to the unpolarized light. So there is also always a very small portion of light that is generated from this laser which is not polarized. The output power, so in this case 10 milliwatts, 1 over E squared beam diameter. So this is the diameter measured when we measure the beam profile. So this is the intensity of the beam, of the Gaussian beam, right, versus the cross section, right? So we measure the beam diameter at the level of 1 over E square of the intensity. So this is around 13.5% of the peak intensity. So in this case, it was less than 0.7 millimeters. And the manufacturer also provides the divergence expressed in milliradians. 1.2 milliradians means that the beam will diverge by 1.2 millimeters over propagation distance of 1 meter. LMS here means the longitudinal mode spacing. So this is something that we call FSR. So this is 320 megahertz. So you can guess that this laser will generate most likely more than one longitudinal mode, because the mode spacing is much smaller than the gain bandwidth. Noise 1%, so this is probably some amplitude noise. And the operating voltage here is 3.1 kilovolts and the current 6.5 milliamps. So we deliver almost 20 watts of power, and we get 10 milliwatts of output. So the efficiency is very low. But on the other hand, we get very nice parameters of the line width. So I said earlier that there is a component of the helium neon laser which is called the Brewster window. So it is placed here on both ends of the resonator. So it's not directly part of the resonator because we have these mirrors here. But the Brewster windows are responsible for the linear polarization of the light that is at the output of this laser. So the principle of operation of this Brewster window is as follows. So from the Snell's law, we know that if we transmit unpolarized light through a glass plate, or this might be just light polarized in both directions, so just two orthogonal polarizations. If we transmit this kind of light through a glass plate that is placed under a certain angle, one of the polarizations will be reflected and the other one will be transmitted through the glass plate. So this this graph here shows the reflection coefficient for different angles of incidence when we have the refractive indices of the material at the level of 1.5 and the refractive index of air equal to 1. And then at around 55 degrees, we will have a minimum here, which means that we have zero reflection coefficient from this plate for one of the polarizations from this RP. So it means that the P polarization, so this one of the polarizations, will be fully transmitted through this glass plate, and all the rest of the light, so the other polarization, the orthogonal one, will be reflected. So this occurs at a very specific angle, which is called the Brewster angle, and this this is related to the difference between the refractive indices of the glass plate and air, because of the boundary of the two media that have different refractive indices. So by this kind of reflection, we can easily polarize the light. So when we place two of these plates inside the laser, they will act as polarizers, because only polarized light will be transmitted through this plate, and all the rest will be reflected, right? So it will be just thrown out of the resonator. So by doing that, we will have only polarized light at the output of this laser. So what you have seen here, so there are two versions. So one is unpolarized. So this one has no Brewster windows, and this one, the more expensive one, has Brewster windows incorporated in the resonator. And you can here you can see what is the, let's say, efficiency of these Brewster windows. So 500 to 1. So as a consequence of the, so the applications are of helium neon lasers are the consequence of the parameters of the radiation that is generated by this laser. So we have a very stable and narrow line width. So by having that, we have a very long coherence length. So that's why Heine lasers are used in various aspects of metrology, like interferometry, like very precise measurements of dimensions of objects, like positioning of machines, geometry of machines, sub-nanometer measurements of displacements, vibrometry, so measurements of vibrations. For example, we can measure the frequency of vibrations of objects, the velocity, and the direction of movement. And we can also measure the frequency. So helium neon lasers are very often used as optical frequency standards. So especially the lasers at 3.3 and 633 nanometers. So in the national offices of standards, so for example, in the US, they have the NIST, so which stands for the National Institutes of Standards and Technology. In Poland, we have GUM, which is Główny Urząd Miar. They have various kinds of standards for metrology, and for example, they have a helium neon laser, which is just a standard of the frequency, of the optical frequency. This is, of course, a stabilized laser, but this can be used as a calibration device for other types of lasers, or just a reference to compare between different lasers. This is an example of a laser vibrometer. So we have the measuring head, which consists of a Heine laser, and then we have all the rest of some data acquisition and so on. And these vibrometers enable us to measure, for example, vibration of various objects, like cars, for example, during the manufacturing of components of the car, like engines, but also musical instruments, for example, and so on. Maybe there will be opportunity to say a bit more about applications later during the semester. Okay, so the next important gas laser is the CO2 laser. So this is the second most important laser, and this is a molecular laser. So the the emission of light occurs from the CO2 molecule. So we have one atom of carbon and two atoms of oxygen, and in general, the energy level structure of the CO2 laser originates from the fact that this molecule can move in different ways. So we have several vibrational modes of the CO2 molecule, right? So they can just linearly stretch, asymmetrically stretch, or stretch symmetrically, or just asymmetrically, like kind of a degenerate bending. And all these vibrational modes, they can, of course, they of course are responsible for the presence of different energy levels in the structure. So if you look on the energy diagram of the CO2, then we will have a number of energy states, which are the consequence of the fact that this molecule can move in different ways, right? So it can be stretched, bent, and so on. So all these movements can store a different amount of energy. And the system is also similar to what we had in the helium neon laser. So usually the CO2 laser contains a mixture of carbon dioxide and nitrogen. And nitrogen is responsible for absorbing the energy. So when we excite the discharge, nitrogen absorbs the energy. We excite nitrogen, and nitrogen collides with the CO2 molecule and transfers the energy to the CO2 via these collisions. And depending on the wavelength that we want to achieve, we have different possibilities. So 10.6 micrometers or 9.6 micrometers, or also 4.3. But the most common is, of course, 10.6. So by that we can have a transition, transition that generates a photon at 10.6, and then we have relaxation to the ground state, and also some kind of intermediate levels before relaxing to the ground state. So this is also a 4-level system, and these the spectrum that is generated by a helium neon laser is a consequence of this energy diagram, because these levels here, they are, as you can see, they are plotted as a one line, but actually this is not a one level, but a group of levels And this is the shape of this level in more detail. So this is like a group of 10 levels. So we have 10 different transitions here between these levels actually. So that's why the spectrum consists of multiple lines. And in the case of the CO2 laser, we distinguish two branches, so-called P branch and R branch. Right, so we have two branches because they correspond to different transitions. So the P transitions here, and the Q transitions are R transitions here. So the spectrum of the CO2 laser will always look like that. So this will be just a very characteristic signature of a CO2 laser, and this originates from the fact that these energy levels are not just single levels, but they are just a group of many rotational levels. So the typical structure of the laser, CO2 laser, is very similar to the helium neon laser. Maybe the one difference is that sometimes if the laser is operated at a high power, there is a water jacket used to cool the tube. That's one thing. And the other thing is that since the laser generates light in the infrared spectral range, like 10.6 micrometers, this is a quite long wavelength. So typical glass based on silica is not transparent to this wavelength anymore. So these windows, these Brewster windows, they need to be made of glass that is transparent for infrared. So usually zinc selenide is used as this output window. It might be also germanium, but most of the cases zinc selenide. These are glasses that have a high transmission in the infrared. So if we would put just silica glass, this wouldn't work. The tube can be made of any kind of glass, but the windows need to ensure the transmission. And of course, the anode and cathode. And the gas CO2 lasers can be excited either with DC voltage, but they can also be excited with high frequency excitation, so RF excited. So then we have the plus minus, right, excitation. So this can induce pulse operation of the CO2 laser, and we can obtain a lot of power. We can have also a simple structure with fixed mirrors directly to the resonator, very similar to what we had in the helium neon laser. And these two examples here, let's see, 1 and 2, they show the typical construction where we want to tune the wavelength of the laser, let's say the frequency of the laser. So one of the mirrors can be placed on the piezoelectric transducer. So this PZT here, when we apply voltage to this PZT, it will expand, right? So it will push the mirror towards the front. So it will slightly shorten the resonator. So it will increase the free spectral range. So by that, we can slightly shift the spectrum of the laser. And since we know that the spectrum consists of these two branches, so we have many lines. If we want to select these lines, one can use a diffraction grating inside the laser that will act as a filter, because the diffraction grating will reflect different wavelengths under a different angle. So when we place this grating under a proper angle, we can ensure that only a certain wavelength, a specific wavelength that we choose, will be reflected by this grating back to the resonator. But the rest of the wavelengths will be just reflected under a different angle, and they will just exit the resonator. So by doing that, we can filter the wavelength that we want. So all the remaining wavelengths will be reflected, but only one wavelength will exist in this configuration. If we have the simple scheme of a tube with fixed mirrors, then you can do nothing, but it's a more simple structure. So the RF excited CO2 lasers can be also realized as waveguide structures. So made of ceramic walls. So we have no tube, but just kind of ceramic structure with side walls and top walls, and two mirrors directly bonded to this waveguide. There are several advantages of this solution. I will go to this in just the next slide. But the issue with this construction is that waveguides can have transverse modes. Okay, so depending on the construction, we can have the TM00, but sometimes we will have higher order modes generated from this laser. So this is something that also needs to be considered. And these CO2 lasers, based on the ceramic resonators, these waveguide lasers, they can be made as slab lasers. So we can scale the dimension of this waveguide. So for example, we can increase the area, but keep the distance between these electrodes. So, and by playing with the pressure, we can relatively easily increase the power, the output power of the laser. So this curve here shows an example of the output power of a CO2 laser versus delivered RF power in the waveguide laser with some dimensions of the waveguide and the proportions of the mixture. And what is the increase of power for different pressures. And in case of the waveguide lasers, sometimes there is a construction used based on an unstable resonator. So this is something that you can see here. So we have the slab. So we have the top layer and the bottom layer of the ceramic. We have the rear mirror here, but the output mirror covers only a part of the output beam. So the output beam here exits the resonator by just missing this mirror. So the aperture of the mirror is smaller than the mode inside this laser. So this is basically an unstable resonator. And because of the high power, as you can see, there is water cooling to cool this top and bottom layer of the ceramic. Interestingly, this construction gives us also the possibility to scale the output power by, for example, multiplying the number of channels, and we can do some arrays or even two-dimensional matrices of structures. So this leads to pretty high power operation of CO2 lasers. And these slab constructions are very often used nowadays, even nowadays in industry. So the most prominent manufacturers are, for example, Rofin, Coherent, or Trumpf. They manufacture these kind of workstations with high power, sometimes high power, but sometimes medium power lasers. And the CO2 lasers are very widely used in laser processing of materials. So their most numerous application is just processing of materials. So these cutting, drilling, marking machines based on lasers, they use a CO2 laser. I have once visited a institute where they developed a huge CO2 laser. So this is a small picture of the laser, but this laser was occupied at the area of, I think, like a half of the soccer playground, and it generated an enormous power of 36 kilowatts, and it was a pulsed laser. And this laser is then used for generating of a UV, extreme UV light, which is afterwards used in lithography for manufacturing of semiconductors. So the company of called ASML from the Netherlands is using this kind of lasers. Okay, so the next group of gas lasers are excimer lasers. So as I said at the beginning, noble gases like xenon and krypton, they usually don't form chemical compounds, but in the excited states, they can form some kind of very temporally bound molecules, which are called excimers or exciplexes. So the typical compounds are like xenon, chlorine, or krypton fluoride. And what is important about excimer lasers that you need to remember that excimer lasers generate only in the UV region. Okay, so that's why they are so interesting, because they provide ultraviolet radiation. So the most popular compounds like argon and fluorine 193, krypton, chromium, and chloride 222, krypton fluoride 248 nanometers. So these are pretty short wavelengths that are also very useful in many applications. So if we want to have a quite simple and robust, reliable UV source, then the excimer lasers is a pretty nice solution. Yeah, I took this picture from Wikipedia, but it very nicely shows the emission of noble gases. As you can see, the neon, which is red, but in argon, krypton, and xenon, we see some visible, but of course, and visible violet radiation. But of course, the most of the transitions are in the ultraviolet range. So the typical parameters of the excimer lasers. So they are usually high power lasers. So we can generate high powers up to hundreds of watts. These lasers are pulsed, so we drive them with the pulsed excitation to provide enough power to excite these atoms to form these excimers. So that's why we cannot constantly keep this medium excited. We just need to pulse this excitation with quite small repetition rates at the level of hertz up to kilohertz. But in turn, we get a huge pulse energy up to 1 joule and peak powers up to gigawatts. But when working with excimer lasers, we need to remember about two things. First of all, these gases are poisonous. And the second thing is the risk of some doing harm because of ultraviolet light, because this is ultraviolet, and this is, let's say, poisonous to us because it's phototoxic, so we can have some problems with our vision and eye damage. And the second thing is also skin cancer. So when working with these excimer lasers, we need to take some precautions and wear, of course, safety glasses and have some sensors of leakage of, let's say, these noble gases. The applications of excimer lasers include mostly materials processing with laser ablation. This is because the very high power and very high energy of the light, because this is UV. So we can induce laser ablation, so just evaporation of the material as a result of interaction between the light and the material, right? So excimers are used for processing of, for example, semiconductors and other types of materials. So they are used in drilling, but marking, but making also some kind of textures of different materials, and also manufacturing of semiconductors using photolithography and microlithography because of the short wavelength. So because of these short wavelengths, we can, in the lithography process, we can make quite small structures. So also in semiconductors. Yeah, and some pictures, fancy pictures of structures made using an excimer laser. So for example, some kind of lab-on-chip devices where we make these channels on some ceramics or other type of materials, and also cutting of bioimplants, for example, like coronary stents made of polymers, and so on. Okay, so this was all about gas lasers. So this is generally a very short overview because we don't have enough time in this course to go more into the details, but I think I have shown you the basics of the typical setups of gas lasers and the let's say principles of operation of helium neon, CO2 and excimer lasers. There exist, of course, many other types of gas lasers, but I mentioned only about these three most important. There is a little bit more about gas lasers on the master course on advanced applied electronics, but if you decide to continue your studies, then we will have the opportunity to meet once again and speak a little bit more about these lasers. So since I have some time left, I will start the topic of semiconductor lasers. So the next group of lasers that we will explore, and the next will be solid state lasers probably. Okay, so as you can guess, semiconductors and semiconductor lasers play a really important role in general optoelectronics, right? Because we have plenty of semiconductors used in optoelectronics, like LEDs, but also photodetectors. And the semiconductor lasers are the most numerous of all lasers. Maybe you remember the slide that I was showing on the first lecture about the market share of different types of lasers among all lasers. So the market share of semiconductor lasers is around 40%. So the 40% of all lasers around the world, when we consider the revenues, are semiconductor lasers. So this is a huge market, which is really important. And this is a huge market because there are many applications of these lasers. So first of all, optical fiber communications. So as I said, when we have internet at home from the fiber, there is at least one laser at our home because we have a laser in our router, or at our router at home. And there is another laser on the other end of the optical link that transmits data. We have barcode scanners, printers, CD players, DVD players, Blu-ray players, and so on. They are also used as pumps for other types of lasers. So when you see somewhere a fiber laser or a solid state laser, then it will use a semiconductor laser as a pump. So every fiber laser on the world, and we have millions of them probably, will need at least one semiconductor laser. And the semiconductor lasers are so popular because they have many valuable properties. First of all, they have a very high efficiency. E to O means electrical to optical, even up to 50%. So when we deliver 10 watts of electrical power, we will get 5 watts of optical power. So when we compare it to the gas laser, where we deliver 10 watts and we get 1 milliwatt, this is just an enormously high number, right? So we have a very high efficiency. Second thing, they have a very small size. So the semiconductor structure has the size of some micrometers. So the whole device can be closed in a housing that has some few millimeters. We pump them electrically. So this is really easy because we just need a stable power supply, just a current source. And by that, we can just pump the laser. They require low voltages, few volts, like 2 volts per one semiconductor laser, and currents at the level of milliamps up to tens of amps if this is a high power laser. We can modulate them even up to 10, 20 gigahertz. So they can be used for data transmission, for example, with these modulations. And they also cover a very broad range of optical frequencies. So from the visible to the infrared. Maybe it's a little bit worse in the UV, but anyway, if we want to have a visible or infrared laser, then it's quite easy from the semiconductor. And they can also provide a very good beam quality, so something which is close to the TM00. So from this image here, you can see that they are basically ideal lasers. So why do we need other types of lasers if semiconductor lasers are so beautiful and great? Yeah, as we say, there are no free lunches, so there is always a trade-off between some parameters. So in general, semiconductor lasers have all these great, excellent properties, but on the other hand, they have issues with multi-mode, multi-longitudinal operation and broad line width. Okay, so the resonators of the semiconductor lasers, they are very low finesse cavities. So they have a broad bandwidth, but the broad line width, but additionally they, because of the short lifetimes and so on, they have broadened lines. So the line widths are they are even incomparable to gas lasers. So when we have kilohertz or hertz line widths in gas lasers, semiconductors have megahertz line widths. So so this is a very huge problem with semiconductor lasers. There exists some specific types of lasers, of semiconductor lasers that have a narrow line width with some fancy resonators. So they can go down to maybe 10, 20 kilohertz line width. But in general, intrinsically, they have megahertz or even gigahertz line width. So I assume that you're familiar with the basics of semiconductors. So this is just a formal image that I have to show that what is the difference between conductors, semiconductors, and insulators. So semiconductors have a small band gap between the conduction band and the valence band. So they are on the scale of conductivity, they are located somewhere between conductors and insulators, right? And what is important in semiconductors is that we can dope them, right? So by doping, we can modify the Fermi level. We can modify the parameters. So by introducing a donor impurity to, let's say we consider now silicon, okay? We can change the energy band structure by adding these impurities, which are just dopants. So when we have silicon, we can add a donor impurity, which is the element from the fifth group. So for example, phosphorus or nitrogen, then we will have one extra electron. And this extra electron can be easily lost at the conduction band. That's why we move this Fermi level closer to the conduction band, right? If we replace one silicon atom with a acceptor impurity, for example, an atom from the third group like boron, it has three atoms, three outer electrons. So we will have one electron missing. So we will contribute a hole here to that. So that's why we move the Fermi level closer to the valence band. So by that we can modify the parameters. So when we have a so-called n-doped semiconductor, so which is the doped with donor, and a p-doped semiconductor, which is doped with an acceptor, when we join them together, we can create a p-n junction. Okay. I am saying that because I am in the defense committee of electronic and computer engineering, and I know that some students don't know what a p-n junction is on the defense. So that's why I thought that it's worth to show this kind of image. So when we make this p-n junction, which is just a typical diode, we can also use it for electroluminescence. So if we make a LED, so this is a light emitting diode, the difference between just an LED and a normal diode is that when the when the recombination occurs here in these electrons in the boundary of these two semiconductor types, the recombination process is emitting light, right? So we have emission when the electron recombines from the conduction to the valence band. And this is the principle of LED. But if we close this LED in a resonator to force stimulated emission, then we will create a laser. So I will go back maybe quickly to just the list of most important semiconductors. What are used in optoelectronics? Of course, silicon, but also germanium, and aluminum, gallium, indium, and also phosphorus. Maybe these are the most popular elements, and they form compounds. So the 3,5 compounds like gallium phosphide, gallium arsenide, indium arsenide, indium phosphide. So these are typical semiconductors that are used for making lasers. And a typical semiconductor laser is a so-called edge emitting laser. So when we make this p-n junction, so we have just two layers of semiconductors. So we have the P and the N junction. So on the boundary between these two types of the semiconductor, we will have this recombination, right? So this is the active region, which is here. And we have usually emission from this edge. So the resonator is formed in this direction, in this axis. So we have the end facets here. So we can have mirrors deposited on these facets, or we can just have a mirror because of this so-called impedance unmatching, because the index of refraction of the semiconductor is quite high at the level of 3, maybe 4, while the index of refraction of air is 1. So we will have a huge mismatch of the refractive indices. So we will have a reflection from the boundary. So this will be at the level of 30–40%, which is completely enough to make a laser. And we have these electrodes. So we have the top electrode and the bottom electrode. So when you connect the power supply, we will have the emission from the edge. So that's why this is called the edge emitting laser. And additionally, this is a homojunction. So homojunction means that this is a p-n junction made of the same type of semiconductor. A typical output power against current characteristic of a semiconductor looks like that. So when we increase the current, at the beginning, we will have, at low currents, we will have domination of the spontaneous emission. So we excite the, excite the electroluminescence, we have recombination, we have emission of spontaneous photons, but still we don't have stimulated emission. But when we exceed a specific value, which is called the threshold current, then suddenly we increase the number of photons, which are photons emitted in the stimulated emission process. And then the increase of power versus the current that we drive is linear. So basically, this is just a linear function. So when we describe the output parameters, then we usually need 2 points. So we need to have this point, and then we can easily calculate any power at any current because this is linear. And you will measure it on the laboratory. As I said, the efficiency is usually quite large because of course, the efficiency understood as the output power to the input power. So the input power is electrical power. And we apply, let's say, let's assume that the one emitter needs 2 volts and requires, let's say, 10 amps of current. And we can get up to 10 watts of output power from this kind of laser. So we deliver 20 watts and we get 10 watts of output power. So this is a huge efficiency because this is up to 50%. And you can define some coefficients that describe the increase of power for the increased current, right? So we increase the current. This is delta E. And we will have some delta P, right? So the increase of power for the increased current on it, of course, in this linear regime. As I said before, the simple example was the homojunction. So this is the same type of semiconductor forms the both layers of the p-n junction, but more efficient diode lasers are based on heterojunction. So heterojunction is formed between 2 different semiconductors with different band gap energies. So for example, we can use gallium arsenide and aluminum gallium arsenide, for example, right? And one of the semiconductors is sandwiched between 2 cladding layers of another semiconductor. So for example, here we have gallium arsenide, which is sandwiched between aluminum gallium arsenide layers and some substrate. So this is a typical heterojunction laser. Of course, depending on the specific requirements, there might be some more complicated structures with much more layers, but generally we have this active region, which is here made of one type between the one type of semiconductor, and then we have the cladding layers of the different semiconductor. So this is also worth to mention, what to remember, that the most efficient lasers are heterojunction lasers. So we don't use just one semiconductor, but we use at least two semiconductors. And what is the most important difference between a laser diode, so a semiconductor laser, and an LED, so a light emitting diode? So there are two fundamental differences. So the first one is in the power versus current characteristics. So in case of the LED, we have only spontaneous emission. So spontaneous emission is linear. So we don't reach the point where we have the generation of stimulated photons. But when we increase the current, we just linearly increase the output power. But in lasers, we have this threshold current. So we have this threshold above which we have stimulated emission dominating over spontaneous emission. So we have a much faster increase of the output power versus the drive current. And the second important difference between an LED and a laser is the spectrum. So the LED has a much broader spectrum than a laser, because the laser, as we know from the, let's say, even the Shawlow-Towns equation, the laser will have a narrowed line in comparison to free spectral range of the cavity. So when we have the LED, the emission is dominated by spontaneously emitted photons, which will have a random phase and random distribution of the parameters. So we will have a distribution of frequencies of wavelengths, while when we have the laser, we will have a much narrower line. However, still in semiconductor lasers, this line is much wider than in other types of lasers. Okay, so I think I will stop here, and I will continue with the types of resonators used in semiconductor lasers next week. So I will stop here on this slide, which shows the typical emission wavelengths for different semiconductor materials. So here you can see what wavelengths can be covered by different materials. So in most typical applications, like in the telecom industry, we use indium gallium arsenide, for example, or most likely, because this covers the range of 1.5 micrometers. Okay, so that would be all. If you have any questions regarding this lecture, you can just write me an email, because I will be on a conference from Tuesday until Sunday. I will be unavailable on the phone or Zoom, but I will of course respond to emails, and the next lecture will be held just normally online on Zoom, and I will send you the link. Okay, goodbye.